And come up to the board and show me a short way of writing the multiplicative identity. Ricky? What's a short way of writing the multiplicative identity? That's right, that's a good start. All right, an I with a multiplication sign.
Project Seed is really something different. This is a situation in which people from the highest echelons of the university world and the world of industry go directly into the ghetto or the community on a daily basis in a non-research, non-consultative role. We have children in our project with IQs of 80 who professional mathematicians are willing to state could do graduate work at a major university if they could continue in the project. So the whole concept that IQ measures meaningfully for the disadvantaged child has been laid aside. Our project believes that there are the same percentage of poets and philosophers, journalists, engineers, mathematicians, scientists in the ghetto as there are anywhere else. And when we look at a class, we are thinking of these children in terms of this kind of aspiration. And they sense this immediately and they respond accordingly.
Well, these are all words we use in algebra. What is addition and multiplication? Brenda? Operations. These are operations. How do we write the additive identity? How do we write the additive identity? DeJoyce? Just tell me if we received DeJoyce. Sorry. 0 equals, all right, what is it? All right, we write I and what else? I plus. Who can tell me how we work with these things? What is a sentence? Let's say, suppose we started with a 7 and we added the additive identity. Write on your papers, what is that going to be equal to? Write that down on your papers. 7 plus the additive identity. Okay, Keith, what is 7 plus the additive identity? 7 plus the additive identity is 7. Let's see if we can make up another sentence like this. Who has a number? Any number at all? David.
140.
140? All right, what's the next thing I'm going to write? Show me on your fingers. The next thing I'm going to write plus, what's the next thing I'm going to write? Who can tell me? Brenda? All right, an identity? What kind of an identity? Additive identity. What's the next thing I'm going to write? Show me on your fingers. The next thing I write. All right, and equals. What's the next thing I'm going to write down? Show me on your fingers. The next thing I write down. It's sort of hard to show that on your fingers. What is it, Gregory? 140. All right, I want to generalize these two statements. What was that word I just used? What was that word? Denise. Who can spell that word for me? Linda?
G.
G. E.
N.
N. E.
R.
R.
I.
I.
L.
L.
I.
Z.
E.
E. Brenda, you disagree with something. What's wrong?
Erase the I after R and put an A.
Erase the I after the R and put an A. Okay. Is it all right now? All right, it's all right now. They're agreeing to that. What do we mean by generalizing something? What does that mean anyways? Who can explain that to me? Tony? You can do something with a Greek letter. That's right. Any other way?
Project SEED brings graduate mathematicians into elementary school classrooms and permits students, particularly those considered low achievers, to explore algebra with men and women who are experts. In addition to a knowledge of mathematics, the SEED specialist uses techniques which are key to the success of the program. They include encouraging the shy student to express and defend his own ideas, and checking on individual progress by circulating the classroom.
Okay, Anthony's having his fingers hurt today. He can't write. He knows the answers. Okay, Anthony, what was your way of generalizing these sentences for me?
Beta plus.
Beta plus. Additive
Equals beta.
equals beta. All right, that's fine. That's one way of generalizing it. Who had another way of generalizing this? Who had another way? Myra?
Zeta plus identity plus equals zeta.
Zeta plus the additive identity equals zeta. How many people had this or something like this? Raise your hands. All right, what does this sentence mean here to me? What does it mean to have, I don't understand that. You just put a letter in a sentence like that, zeta plus the additive identity. What does that mean? Ricky?
It means that if you, zeta could be any number, so zeta could stand for any number that you put there.
Zeta could stand for any number that you put there. That's good, Ricky. That's very good. Gregory, you want to say something?
And those two things, they're not number form. If they were number form, they would still be kind of form. So 140 was 7.
All right, that's good, Ricky. Gregory, you're saying if they were in number form, they'd be of the same form as these two. Okay, what is the additive identity? What number does that equal? What number does that have to be? Show me on your fingers. What number does that have to be? A 1, 0, 0, 0, 0, 0, 0, 0. It equals a 0. I don't understand that. I thought that identities would have to be equal to 1. Somebody told me that an identity was always equal to 1. I just don't understand that. Calvin, what's wrong? Why can't that be a 1?
Because the identity of multiplication stands for 1, and identity of addition is 0.
All right, you're saying the identity element for addition is 0, and this is the identity element for multiplication. Why can't the identity element for addition be a 1? I want it to be a 1. Why can't it be, Anthony?
Because if 0 plus 6 equals 6, then, and 6 plus 1 equals 7, they're not the same thing.
They're not the same thing, right. I see, and you want the thing to stay the same. Okay. So it has to be a 0. What about the identity element for multiplication? How do we use that? Suppose you take an 8 times some kind of an identity, and you get an 8. What would that have to be? What kind of an identity? Clifford? This has to be a plus. Whoops. Some people are disagreeing with that. Clifford, you want to call on somebody who disagrees with you? Quickly, Clifford, just call. Keith.
Raise the plus sign.
Erase the plus sign.
And put an X.
In the summer of 1970, the United States Department of Education funded a training program for teachers with graduate experience in mathematics. At this time, they are given an opportunity to observe SEED specialists working in New York City classrooms and to take part in the instruction. New insights are gained as to how much students might achieve in algebra, considered a difficult subject by most teachers. They explore different ways of presenting the concepts involved.
Another type, also in SEED, who may kind of force the subject and lead the children into perhaps thinking that they are discovering something. Then there's another type I have observed who would see the direction that the youngster is going and then lead him and do an adequate job of it.
You think that it's wrong to lead kids to discover what you want them to discover and
No.
let them think that they're discovering it on their own?
No, I think it's all great, but I think we should also realize the difference in the approaches of the different personalities of type of teaching that's going on.
I think also, like, a good example of that was the other day when I was teaching a class, and the topic that I wanted to cover, matter of fact, the class got me there before I got there, you know, and that, you know, that was the best way of, you know, teaching that topic.
They discovered it on their own.
Right, well, they answered the question, you know, they had two varying answers, and that was what I wanted to show anyway, and so we went from there.
If she had not been proficient in mathematics, then she would not have been able to guide the student. And therefore, it is necessary that a teacher in seed have a very strong background in mathematics.
Muy bueno. Very nice. Good. 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 Did you remember that, or do you know how to do it? You know how to do it. I knew you did. I just wanted to see if you... Okay, very nice. Who'd like to come up to the board and write it on the board? Someone tall. Reno? What? 16. 16. Okay, can you come write it on the board? Yo quiero que venga aquí para escribirlo aquí. You agree?
Yes.
Okay. Who knows 2 exponentiation 3? Let's see, Diane? Do you agree? Okay. Show me on your fingers. What is 2 exponentiation 2? Show me on your fingers. I see 4, 4, 4, 4, 4, 4, 4. Jose, how did you get 4?
Because 2 exponentiation 2, it's like 2 times 2 equals 4.
Okay, how many people agree with that explanation? Good. Well, who knows 2 exponentiation 1? I see fingers, that's good. Gerard? 2. Who knows what the next question's going to be? Daisy?
2 exponentiation 0.
2 exponentiation 0?
Yes.
Oh. Okay, that equals 0. No. Patrick. What does it equal?
Because 1.
1. 1? No, it doesn't equal 1. It does?
Yeah.
Who can prove to me that 2 exponentiation 0 equals 1? Because in mathematics, you have to prove things or they don't count. Can anybody do that? Felix, ¿puede?
Quantity 2 exponentiation 0 times quantity 2 exponentiation 1 equals 2 exponentiation quantity 0 plus 1.
How many people agree with what he said? Okay, now we have a true sentence. Who can tell me a way to simplify it? James?
0 plus 1 plus 0.
Put 0. 0 plus 1 is...
Oh, I know.
What?
1 plus 1.
Put 1. You agree?
Yes.
All right. Is that all we can do?
Yes.
Maura?
You could take the 2 exponentiation 1 and erase it, and you could put a 2.
Put a 2. How many people agree that I can erase that and put a 2? Okay. Put a 2 here. What about here? You don't know about there. Well, 2 exponentiation 1, when it was over here, it equaled 2. What do you think it'll equal when it's over here?
2.
I think that pretty good guess. Okay, now what do we do? Now what do we do?
You gotta put a 1 because 1 times 2 equals 2.
Oh, do you all agree with that? I gotta put a 1 where? Iris?
Over there in 2 exponentiation 0.
It has to be a 1. Good. You proved it. We did 2 exponentiation 3. We did 2 exponentiation 2, 2 exponentiation 1, 2 exponentiation 0, and it's all over. No. Oh, Edward.
2 exponentiation -1.
How many people knew that -1 would come next? Could you make a sentence out of it to find out what it would be?
Yes.
How many people could do that? Who would like to do it? Gerard?
Quantity. 2 exponentiation -1 times quantity. 2 exponentiation 1 equals 2 exponentiation quantity -1 plus 1.
This factor of expectation is enormously important. In fact, many teacher training institutions in the United States today feel this is the major task in preparing teachers to work with disadvantaged kids. Kids seem to sense instantly what your own expectations for them are. You expect little, you get little. And our program provides a superb model of children doing something that the average college graduate has trouble with. This tends to verify the basic theory that we have, that self-concept is the fundamental basis of intellectual performance in all areas.
You know, I could mention specific children who we didn't get anything from them in the beginning of the year. And now, for the first time in their academic career, they're able to compete with children who are more advanced than them. Certain children have just slept for the last 5 years because they couldn't answer. They didn't know. But in this, for some reason, everybody's equal. It equalizes the whole class.
Yeah, Harold. In other words, arithmetic is also taught in the classroom, not just the seed project.
That's right. Arithmetic is also taught. But I think what we do, our algebra, even though it isn't arithmetic, causes the arithmetic to get better because they see occasionally we have to do arithmetic. But it's buried in some interesting mathematics. So they say, oh, well, gosh, you know, I like to do this now. It's not just, you don't concentrate on just arithmetic because they've sort of failed at that and they say, oh, I can't do that. But then when they can do it, it's great.
But it's really inspiring to see how every student can do these problems. Mathematics is really a very simple thing to do, and especially when taught by a professional, every student can participate. Today I saw a class where there was a girl who could not speak a word of English, could speak only Korean, and she was able to answer every problem because the problems are not really verbally oriented. They all have to do with numbers that every child can understand. And children have respect for mathematics. They're very excited by the fact that they can do this. It looks impossible. They're very happy with it.
As the program goes on, we encourage the students to verbalize more and more. We encourage them to explain their answers. We encourage them to use precise mathematical language so that by the end of the year they are much more verbal than when we start.
Many people are doing summations now, and you can get into infinite summations of, say, negative exponents. And we have in the past arrived at things like summation is I equals 1 to infinity of 5 times 10 to the negative I equaling 5 ninths, and various limits with exponentiation. Or a different path that it has taken is to introduce logarithms and roots as inverse operations of exponentiation. And when you get into this kind of thing, you can also get into irrational numbers, because you can let this be a fractional number c over k,
This leads to 2 to the c over k equaling 8. And by the multiplicative law of exponents, you have 2 to the c equals 8 to the k. And they get a fractional number like 3 over 1 or 6 over 2. And then you just simply give them one like that. And they get 2 to the c equals 10 to the k. And then you can actually get them to find it on number line, where they will see it has to be between the log 8 to the base 2 and the log 16 to the base 2. Or between 3 and 4. Yeah.
Susan, I actually saw or heard a student that did something that my college students couldn't do on this log 2, log 8 base 2, log 16 base 2. This student actually was interpolating. They noticed that the answer to log 8 base 2 is 3 and the other was 4, and so they said, well, let's see now. Log 10 is 2 away from 8, and so that must be, and there's 8 between them, so it must be 2/8 of the way, and it's 3 1/4, and I just went out of my mind. This is interpolation. It's something that college students can't do, and this kid had done it naturally.
Plus 7.
Without any explanation.
Plus 9. Plus 10. Plus 11.
Plus 11? Why? Okay. What goes next after that, Randolph? What goes after that?
Equal.
An equal? Well, that means we're going to stop at 11?
This one summer training program has helped start more than 200 new seed classrooms spread out from New York City to Seattle, Washington.
What was this last number? Where did you see it?
The highest.
The highest? What do we call it? What's the special name that we gave to that number?
Explanation.
The special name that we gave to that number? Well, let's see. Call on somebody to help you out then.
Okay. Upper limit.
Right, we call 11 the upper limit. And that's where we stop.
I'd like somebody to read this for me, very loudly. Patrick.
Alpha exponentiation beta equal pi.
Very good. Who can undo this the left way? That's harder. But you can do it. Iris.
Pi. You said the left way?
The left.
L. Alpha equals beta.
How many people agree with this? Very good. Okay, now, who remembers what I told you this L stands for besides left? It's a word that it stands for besides left. Fridolin? Logarithm. Can anybody spell logarithm? L? O? G? Z? A? R? Logarithm. G? No. I?
T.
Oh, you're so good.
H. N.
That would be a very good idea. They spell it very strangely. They spell an M on the end. How do we write that very short? Instead of having to write logarithm out, how can we make that very short? James.
Log.
Log. Right. Who can write this sentence in high school, university vocabulary using the word log? They write pi log L equals beta in a very strange way. Does anybody know how to do that? Edward.
Log. Pi. To the base alpha equals beta.
How many agree with that? Oh, very good. Very good. Okay, what I'd like you to do is suppose I write log 32 to the base 2 equals square variable. Who can write this our way using E? This is the hard part. You know how to go from E to L, but it's harder to go from L back to E. Jose.
2 exponentiation box equals 32.
Who knows what goes in this box to make this exponentiation sentence true? 2 exponentiation, what is 32? Let's see, 1, 2, 3, 4, 5, 6, 7, 8 people know it? 9 people? 10 people? That's a pretty hard one. Show me on your fingers what you think it is. Everybody. 1, 2, okay, you got 5, 5, 5, 5, 5, 5, 5, 5, 5. Very quickly. 2 times 2 is what? 4. Times 2? 8. Times 2? 16. Times 2? 32. How many did we use? 5. Okay. I want to know what the log of 1/8 to the base 2.
The project seed techniques presuppose more than one way of finding a correct answer, and they involve the students and their enthusiasm directly in the discovery of as many solutions as possible.
Think you know the answer? Raise your hand. Let's see. James.
We use the Edward law.
The Edward law is a law that Edward made up, right? Now, how are you going to use the Edward law?
I think by putting exponentiation form.
Can you put this in exponentiation form?
Yeah. Box? No. 2.
2.
Exponentiation. Box equal 1/8.
Equals 1/8. Okay, James, what do you think would go in this box to make this sentence true?
-3.
-3. Okay, how many people agree it's -3?
Perhaps many more subjects of high status can use these same techniques. After all, if students in the 3rd and 5th grades can work with mathematical identities, exponentiation, summations, and logarithms, what sort of original work might they do in high school, or later if they go on to college?
How do you know that that's always true? What did you say before? What law did we discover the other day?
Edward law.
Edward's law, that's what it says.